Greetings, and welcome to a journey millions of years in the making. Today, we venture into the heart of a paleontological mystery, a tale written not in stone, but in the very marrow of these magnificent creatures, the dinosaurs. We often marvel at the immense size of some dinosaurs, their skeletons towering over us in museums. But have you ever wondered how these prehistoric behemoths achieved such incredible growth rates? The answer, it turns out, lies deep within their bones, in the often overlooked tissue known as bone marrow. To understand the secret of dinosaur growth, we must first delve into the intricacies of their bones. These ancient remnants hold the key to unlocking the mysteries of how these magnificent creatures lived, grew, and thrived millions of years ago. By studying the microscopic details and the overall structure of dinosaur bones, scientists can piece together a vivid picture of their biology and growth patterns. You see, not all bone is created equal. Each type of bone tells a different story, revealing unique aspects of the dinosaur's life and growth. By comparing different bones, scientists can identify variations in growth rates, health, and even the environment in which these dinosaurs lived. Dinosaurs, particularly the larger ones, possessed a special type of bone tissue known as fibrolamellar bone. This tissue is fascinating because it indicates rapid growth, a necessity for these giants to reach their colossal sizes. The fibrolamellar bone is a testament to the incredible biological machinery that powered these prehistoric titans. Imagine, if you will, a bustling construction site, materials flowing, workers laboring tirelessly. This analogy helps us understand the dynamic nature of fibrolamellar bone. Just like a construction site, this bone tissue was a hive of activity, constantly building and remodeling to support the dinosaur's rapid growth. Fibrolamellar bone was a bit like that, a hive of activity, rich in blood vessels and teeming with cells, all working in concert to drive rapid growth. The presence of numerous blood vessels ensured that nutrients and oxygen were efficiently delivered to the growing bone, facilitating the swift expansion necessary for these creatures to reach their enormous sizes. This type of bone is characterized by a woven, fibrous structure, quite unlike the more organized, layered structure of lamellar bone found in most mammals today. The fibrous nature of fibrolamellar bone allowed for quick deposition and growth, a stark contrast to the slower, more methodical growth seen in lamellar bone. This unique structure allowed dinosaurs to grow quickly, reaching their enormous sizes in astonishingly short periods. The rapid growth facilitated by fibrolamellar bone was crucial for survival, enabling these dinosaurs to outgrow predators and adapt to their environment swiftly. In contrast, slower-growing dinosaurs, like some of their more modestly sized kin, exhibited a different type of bone, known as lamellar zonal bone. This bone type is indicative of a slower, more deliberate growth process, reflecting a different survival strategy and lifestyle. This bone type, while strong and durable, reflects a more measured pace of life, with growth occurring in a series of layers, much like the rings of a tree. Each layer represents a period of growth, providing scientists with a timeline of the dinosaur's life and growth patterns. By studying these layers, researchers can gain insights into the environmental conditions and challenges these dinosaurs faced throughout their lives. Now let's journey deeper into the very core of these bones, where we find the lifeblood of growth, the bone marrow. This remarkable tissue, nestled within the hard exterior of bones, is a powerhouse of activity. Think of bone marrow as a bustling metropolis, a network of blood vessels supplying the building blocks of life. It's here that red and white blood cells are produced, essential for carrying oxygen and fighting infections. The more blood vessels present, the faster the transport of nutrients, and the more rapid the growth. This intricate system ensures that every part of the bone receives the necessary resources to thrive and develop. Take, for instance, the mighty Tyrannosaurus rex. This apex predator, known for its formidable size and strength, has left behind bones that tell a fascinating story. Its bones reveal a network of blood vessels so dense, so intricate, that it rivals the complexity of a modern bird. This dense network indicates a highly efficient system for nutrient transport, crucial for supporting its massive frame. This suggests that T. rex, despite its size, grew at an astonishing rate, fueled by a rich supply of blood to its bones. Such rapid growth would have been essential for reaching its enormous size within a relatively short lifespan. On the other hand, herbivores like Triceratops, while still massive, exhibit a slightly less dense network of blood vessels in their bones. This difference in vascular density provides insights into their growth patterns and lifestyle. This suggests a slightly slower, though still impressive, growth rate compared to their carnivorous counterparts. The Triceratops, with its robust frill and 3 distinctive horns, required a steady but less rapid growth to support its herbivorous diet and defensive adaptations. These differences in blood supply within the bone marrow played a crucial role in shaping the diversity of dinosaur sizes and growth patterns. By studying these ancient bones, we gain a deeper understanding of how these magnificent creatures lived, grew, and thrived in their prehistoric world. Chapter 3. The Warmth Within. The debate over whether dinosaurs were warm-blooded or cold-blooded has raged for decades. This question is not just a matter of academic curiosity, it has profound implications for our understanding of these ancient creatures. Were they sluggish, cold-blooded reptiles, or were they dynamic, warm-blooded animals with high energy levels? Bone marrow, surprisingly, offers intriguing clues. By examining the microscopic structure of fossilized bone marrow, scientists can infer the metabolic rates of these long-extinct animals. The density and arrangement of blood vessels within the marrow can indicate how efficiently oxygen and nutrients were transported throughout the body. Warm-blooded animals like us maintain a constant internal body temperature, requiring a high metabolic rate and a constant supply of energy. This ability allows them to thrive in a variety of environments, from the icy tundras to the scorching deserts, by keeping their internal processes stable. Studies of dinosaur bone marrow, particularly the density of blood vessels, suggest that some dinosaurs, especially the larger, more active predators, may have possessed warm-blooded characteristics. This would mean they had a higher metabolic rate, enabling them to be more active hunters and possibly more social creatures. This warm-bloodedness, if present, would have had a profound impact on their growth rates. Warm-blooded animals grow faster because their bodies can sustain higher levels of activity and metabolism, leading to quicker development and larger sizes. A higher metabolism, fueled by a constant internal engine, would have allowed these dinosaurs to grow much faster than their cold-blooded counterparts. This rapid growth could have given them a significant advantage in survival, allowing them to reach maturity more quickly and reproduce at a faster rate. However, the debate is far from settled. While some evidence points towards warm-bloodedness, other studies suggest that dinosaurs might have had a unique metabolic system that doesn't fit neatly into our current categories of warm-blooded or cold-blooded. Some scientists argue that other factors, such as environmental conditions and behavior, also played a role in dinosaur growth. The climate they lived in, their diet, and their daily activities could have influenced their metabolic rates and overall physiology. The mystery of dinosaur metabolism continues to intrigue paleontologists, with bone marrow providing a tantalizing glimpse into their physiology. As new technologies and methods of analysis develop, we may one day uncover the full story of how these magnificent creatures lived, grew, and thrived in a world so different from our own. Chapter 4. You are what you eat. The old adage, "you are what you eat," rings especially true in the case of dinosaurs. Diet played a crucial role in shaping their bone marrow, and consequently, their growth rates. Herbivorous dinosaurs like the massive sauropods faced the daunting task of extracting enough nutrients from plants to fuel their enormous bodies. Their bone marrow reflects this challenge, often exhibiting a slightly different composition compared to carnivores. The constant need to process large quantities of plant matter likely influenced the development of their bone marrow, favoring a steady, if slightly slower, growth rate. Carnivores, on the other hand, with their protein-rich diet, had access to a more concentrated source of energy. This allowed for the development of bone marrow that could support rapid growth, essential for predators in a world ruled by giants. Chapter 5. A Time of Change. Dinosaurs, like all living things, were not immune to the whims of their environment. Climate and seasonal changes played a significant role in their growth patterns, leaving their mark on their bones. In polar regions, for example, dinosaurs faced long periods of darkness and harsh winters. Their bones tell a tale of adaptation, with evidence of seasonal growth spurts, much like the rings of a tree. During the warmer months, when food was abundant, these dinosaurs grew rapidly, their bone marrow working overtime. However, during the lean winter months, growth slowed, leaving behind telltale lines in their bones marking the passage of time. These growth rings, preserved for millions of years, provide us with a window into the lives of these ancient creatures, revealing the challenges they faced and the adaptations they evolved to survive in a changing world. As we conclude our journey into the microscopic world of dinosaur bone marrow, we are reminded of the intricate connections between life and its environment. From the bustling activity of fibrolamellar bone to the telltale growth rings of polar dinosaurs, bone marrow provides a unique window into the past, allowing us to unravel the mysteries of dinosaur growth and physiology. Thank you for joining me on this adventure. Remember to keep exploring, keep questioning, and keep the spirit of discovery alive. Until next time, may your curiosity continue to lead you to new and fascinating corners of our natural world.